Okay, so now we're going to actually look at deriving these rate equations. We've talked about the theory, we've talked about a lot of theory in this topic so far, and hopefully this video here will help us tie everything together. So we're actually going to start dealing with numbers, seeing how we actually work out the orders with respect to our reactants that we looked at in the last video. And this video really should tie all of that together, and we'll start to, hopefully the light bulb will start to come on. So, deriving rate equations. So how do we actually derive these rate equations? How do we work out the orders with respect to the reactants that we spoke about so far? Well, first of all, we have no choice but to do a kinetics or a rates experiment. Remember I said earlier, these things can only be worked out through rates experiments. There is no other way. When we do that, we will, if you remember right back to the first video, okay, we will get our concentration versus time graphs, something kind of like that. If you remember, what we then said was we would plot various different gradients, excuse my artwork, at various different times, okay, from that concentration time graph. From that then, we can put together a little table of concentration versus time, usually in seconds, in our table, and we can have concentration A, B, and C, and we can have time as D, E, and F, raw for graph. Okay? Now, this is what so that's our raw data. Sorry, apologies, doing this back to front. That's our raw data. From our raw data, we will then plot our graph. From our graph, then, we can take and we can get our rate versus concentration data. So, for example, what I mean from there is I go from there, okay, as I now have concentration versus rate. Rate, remember, is a gradient. Okay, so I will have concentration of A, B, and C, and I will have read off my gradients at A, B, and C, and I will get from there my rate of E, F, and G, let's say. Okay. Now what am I going to do with that? I am now going to take that and I'm going to plot rate against concentration. And this is the new graph that we haven't spoken about so far. This is the graph that is going to allow us to work out the order with respect to a particular reactant. So going back, we've done our experiments and we have got concentration versus time tabulated data. We put that into our graph of concentration against time. We find the gradients at points A, B, and C, and we now have concentration against rate. And then if we want to, we can put that onto a rate versus concentration graph. Okay? And that will allow us to start getting our orders. Right? So, like I said, we now have our order with respect, it might be just to reactant 1. And we will then go back and do exactly the same thing. If we have 3 reactants, we'll do exactly the same thing for reactant 2, keeping reactant 1 and 3 constant but in excess. And then we will do the same again for reactant 3, keeping reactant 1 and 2 constant but in excess. And we will change the concentration of reactant 3. That will give us eventually, after all of that, our overall rate equation. So, I talked about concentration time graphs. If you think about it, if we go right back up to here, we did our experiment and we tabulated our data and then we plot concentration time graphs. And we will get 3 possible lines at A level. Okay? And remember, on concentration time graphs, the gradient is the rate. Okay? So if we look at the line graph A, we can see that's a linear graph. That tells me that the gradient, no matter where I am on that line, is constant. That tells me that the rate is constant. That tells me that no matter what I do to the concentration of R, okay, it has no effect on the rate. The rate is the same no matter what the concentration of R happens to be. Okay? That tells me that it does not tell me that. It tells me that it's zero order. In other words, that means that no matter what I do to the concentration of R, if I get a straight line on my concentration time graph, the change in the concentration has zero effect, no effect on the rate, therefore that is what we call zero order. Okay? If I look at B and C, we can tell that the gradients in B and C, as I go along, are changing. Now, they are either going to be first order or second order. I cannot tell by looking at those which one they're going to be. I have to do some further processing. For A, straight line, zero order, I can tell straight off. The others, I've got to do a bit more work. So, let's go through the process that I talked about on the first page. Okay, so this is our graph. We have concentration time. Hopefully you can tell that no matter what I do to the concentration of R, the rate doesn't change because the line is straight, the gradient is straight, therefore the rate does not change. Okay, I will turn that into a concentration rate graph. Try and predict the shape of this line. Pause the video, predict what shape if I plot my rate against concentration, and that should be just a straight line like that. Now you can easily see that no matter what I do to the concentration, the rate is constant. Okay, so in other words, changing the concentration has no effect on the rate, therefore this is what we call a zero order reactant. R in this case is zero order. So if I double concentration of R, rate stays the same. Halve it, rate stays the same. Treble it, rate stays the same. Very simple. You might also get tabulated data. Okay, so if we look at how do we work it out from there, concentration from here to here doubles, rate from here to here stays the same. Concentration from 3 back to 2 experiment goes up by a factor of 4, rate stays the same. Doesn't matter what I do to concentration, rate stays the same. That's another way to work out your zero orders. Okay, now we can now see how we work out our rate constant. Okay, so my rate constant, okay, very simply, okay, if I plug in my rate, okay, which in this case is that, my order, okay, or my concentration here is 0.2 for this one to the zero order, so that is, okay, and therefore my rate equals K, so in this case my K value is the same as the rate, 2.7 times 10 to the minus 3, and if we did our units as we did earlier, moles dm to the minus 3, s to the minus 1, and we just pick one experiment, okay, and we plug our values into our rate equation for that. We could pick any experiment, it wouldn't matter, the K value in this case, or in any case, will always be the same. Okay, let's look at the next concentration time graph. Here we would plot gradient, 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 okay? We will have our gradient lines, excuse my artwork, and remember our gradient is our rate. So from that, we plot those into a table and then we plot them on our graph, we get a straight line. So in other words, what we're saying here is that rate is directly proportional to the concentration, okay, of R. So if, in other words, if I double the rate, or if I double the concentration, sorry, I double the rate. If I have the concentration of R, I have the rate. If I treble the concentration of R, I treble the rate, directly proportional. And when it's directly proportional, your assumption is that it is, or your deduction is that it is first order with respect to reactant R. Okay, and we would write it as such. You might also get it tabulated. Let's have a look. So from here to here, doubled concentration, doubled rate. From here to here, quartered concentration. If you get your calculator out, if you need it, quartered rate. So therefore, it is directly proportional. Okay, so it is first order, written as so. If I want to work out the K value, the rate constant, I would take 1. So there's my concentration, there's my rate. Okay, rearrange your equation, rate on the top line, concentration to the power of 1 on the bottom line. Okay, and there's your value and there's your units. Pretty simple maths. If we look at this one, we can see it's a similar shape to our previous one, which was first order, and this time, Okay, now we cannot risk it, guys, and look at this graph and go, oh, that's first order. And likewise, we cannot risk it and go and look at this graph and go, oh, that's second order. Okay, never do that. So we will do the same again. We will plot gradient, 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 gradient. Okay, remembering gradients are equal to rates. So we now have a relationship between concentration and rate, concentration and rate, concentration and rate. And we plot that this time, and if we get a graph of this shape of concentration against rate, we can say this is second order. So this is these graphs you need to recognize visually, okay? You don't want to be analyzing them any further. You should be able to pick up zero order of rate versus concentration, first order rate versus concentration, and this is the second order rate concentration graph. They're all very different. Now do be careful if you get an examiner which is being a bit sneaky and we get a straight line. Loads of people will look at that and go, oh, that's first order. It isn't first order, it's second order, because this is concentration squared. Now we get a straight line. So just be careful. Now I've never seen them do this except maybe once in quite a long time, but just have an eye out for it. So all those graphs you should recognize as by eye, okay, as being second order. This one and this one. This one do not go by eye, okay, because it looks very similar to a first order reaction of time against concentration. So this time what we're saying is the rate is directly proportional to R concentration squared. In other words, if I double the concentration of R, the rate goes up by a factor of 4. Okay, or in other words, 2 to the 2. If I have the concentration, the rate is quartered. Okay, so in other words, 0.5 to the 2. Okay, second order. Okay, if I treble it 3 to the 2, it goes up by a factor of 9. Those are how you pick out your second order reactants. So if we look at the table this time, this has doubled. This has gone up by a factor of 4. In other words, doubled to the 2. Second order. If we go from here to here, this has gone up by a factor of 4, going 3 back to 2, sorry, a factor of 4. Okay, this has gone up by a factor of 4 to the 2. 16 if you get your calculator out. That has gone up 16 times. Okay? So, therefore, this must be a second order reactant. Okay? So the order is directly proportional to R squared. And we would write it as so. If we wanted to work out the K value, we take any of the experiments. Okay? So this one, I think we've taken number 1. So it is 1.6 10 to the minus 3 is the rate over 0.2 squared. Remember your units. Okay, it gives me 4 times 10 to the minus 2. And that's how we work out our K value. So now, hopefully guys, all of this stuff's starting to come together. Okay, and you can now see, how do I get my order? How do I work out my K value? How do I get my units from a K value? Okay, now those are all, if you look at all the ones we've done, we've only had one reactant involved. We're going to look at some more complicated ones, okay, in the next video, and we'll see how we get on with those. So let's have a look at this one before we go. Right, this time we've got to work out an overall order. Okay, so how do I do that? Well, remember I said earlier, I want to work it out for R1, R2 and R3. Okay, how do I do it? Well, I'm going to try and find an experiment where only one of those reactants changes and the other ones stay the same. So this is a nice simple one. First one, for R1, I'm going to look at experiment 1 and 2. Because R2 and R3 remain the same. So any change in the rate is only because of R1. That has, of course, doubled. If we look here, this has, of course, doubled. So therefore, you should be able to work out that the order with respect to R1 is, of course, first order. Let's go and deal with R2 now. R2, which 2 experiments? You might even work them out before I say it if you want to pause the video. Which 2 experiments would I use for R2? Well, I'm going to use 1 and 3. Okay, because R3 has remained constant, R1 has remained constant, and R2 has doubled. Okay, if we look at the rate has stayed the same. So therefore, hopefully you can work out that R2 must be having no effect on the rate, therefore R2 is 0 order. Let's go and look at R3. R3, which two experiments am I going to use? I'm going to use 1 and 4 because R1 stays the same, R2 stays the same, R3 has doubled, and our rate has gone up by a factor of 4. So that means that this is doubled, it's gone up by a factor of 4. Okay, so the order must be second order, in which it is. Okay? Now, you will then be expected to write the overall rate equation for that. Remember, R1 was first order, R2 was 0, and R3 was third order. So that would be your overall rate equation. Okay? The overall reaction itself is third order. If you think back to our second slide, second PowerPoint, sorry. Okay? Just the 1 plus the 2. Okay? Right, so there's our equation. Now we're going to work out our K. Now we take any experiment. Normally we would just take experiment 1. So we're going to have K rate equals, so we'll take our rate at 0.022 equals R1, which is 0.1 to the 1, R2, 0.1 to the 0, which is 0, and R3, 0.1 squared. And we'll sub them in as so. Okay, so we can ignore that. Again, we'll do our units. That's our K value, so it's a high K value, very fast rate of reaction. And there's your units, which will be worth a mark in all your questions. Okay. So this one's a little bit different, and then we've got to work out a value. You've got to work out an X value, which is concentration of A. So we've got to deduce the rate equation first. So let's do that. Let's deduce the rate equation firstly. Right. So for A, I'm going to use experiment 1 and 2 because that doubles. B stays the same. If we look at our rate, if you get your calculator out, or hopefully most of you will be able to do that off the top of your head, that has gone up by a factor of 4. So that means that A is going to be second order. Okay, let's look at working out B. Well, I'm going to use this one, 2 and 3, because that stays the same, and that has doubled. This has stayed the same, so therefore B is 0 order. So my rate equation is going to be rate equals K upon A, square brackets always, squared, B, square brackets 0. Don't need to put that in really, but up to you. Next thing, we've got to work out our value of X. So let's have a look and see what we can do there, because we now know the rate equation. So I'm going to choose experiment, I'll just use experiment 3 and 4. It really doesn't matter which ones I use because I know that B has no effect on the rate. Okay, so let's look at experiment, we'll go experiment 4 back to experiment 3. So I'm going to sub in the relative changes of the concentration and the rate to help me out here. So if I look at the rate from there, from 3 to 4, the rate has gone up by a double. So I'm going to put 2 in there for rate. Okay, and then K is a constant, so I can leave that out. All right, and therefore the change in concentration, I'm going to put a question mark in there, squared. Okay, so this question mark represents the change in concentration of A from experiment 4 back to experiment 3. Okay, so the change is whatever squared equals 2, so therefore the square root of 2 equals the change in the concentration of A. So let's just square root 2. So that tells me that the change in the concentration of A is, put an A there, 1.41. So as I go from experiment 4 back to experiment 2, the concentration of A has gone up by a factor of 1.41. So therefore 0.2 divided by 1.41, okay, 0.2 divided by that gives me 0.141. Okay, so my concentration of A would be there at the end is 0.1412. I should probably write 0.14 because everything else in that table is to 2 sig fig. Okay, so I'll just pop the answer up so that I can hopefully prove that I am correct. And you can pause it here for a second, guys, and look at it and go through it. Okay, I didn't actually work out the rate constant. That's my mistake. I skipped that out. But hopefully you can see the rate constant was equal to, that was the rate, and it was 0.1 squared. Okay, so you can go from there. Okay, so if you want to pause that video and have a look at that screen, guys, you can see hopefully everything that is relevant there. Okay. Right, so we'll have a look at this one now. If you want to look at this question, you can probably start doing this yourself, guys. Okay, working out the x, the y, and the z. Remember, please, so many people forget this up here. It gives you the rate equation in this particular instance. You cannot do this equation, or this question, sorry, without the rate equation. Right, let's have a look. So if you want to pause the video and do it yourself, that's fine. I'm going to work through it here. Okay, anyway. Right, so let's first of all work out x. Right, so if we look at, I'm just going to write out my rate equation down here. So it is a to the 1, b to the 2. Right, so here a has remained constant, so I'm going to put a 1 in there, multiplied by b has gone up by gone down by a factor of a half, so it's a half squared, so that's 1 times 0.25. Okay, a half squared is a quarter. Okay, and I'm looking to see what is the relative change in the rate. So I now know that rate equals 1 times 0.25, so the rate has been quartered. Okay, so I'm going to take 1.04 times 10 to the minus 2, divided that by 4, gives me 0.98. Okay, that does not look right. I'm going to double check that. 1.04 times 10 to the minus 2 divided by 4 equals, yeah, it was wrong. Okay, I think I had not put into the minus 2. So that comes out at 2.6 times 10 to the minus 3. So it is that divided by 4. Okay, right, so just a wee lesson there, guys. If you do put an answer in and it does not look right, recalculate. Right, let's have a look at working out what y is going to be. So for y, we'll take experiment 1, we'll just go experiment 1 and experiment 3. Okay, don't really want to use experiment 2 in case I've somehow got that wrong, so let's just use ones where we have the data there. So let's see, first of all, so rate, I'll just write this out again. Rate equals a to the 1, b to the times b to the 2. So we're putting in the relative changes, okay? So from experiment 1 to experiment 3, we have, let me just calculate that. I don't want to get that wrong. So we've got 5.2. 1.04 times 10 to the minus 2 divided by 5.2 times 10 to the minus 3. Okay, so that's halved, should have known that. Okay, so that has halved equals a, well that's what we're after, we're working out the relative change of a times b from there to there. That has, I believe, that is a doubling, yeah it is. So it's a doubling, so it's a 2 to the 2. So in other words, half equals the change of a, which we're trying to work out, times 4. Okay, so if we rearrange that equation, a half divided by 4 equals the change in a. Okay, so 0.5, so it's an eighth, isn't it? Okay, so the change in a from, so if we just do that, equals times 1/8. So therefore, if I do my a starts off at 4.8 times 10 to the minus 2 divided by 8. 4.8 times 10 to the minus 2 divided by 8 gives me 6 times 10 to the, so the new concentration of a would be 6.0 times 10 to the minus 3. Hopefully that makes sense to you. Okay, let's do the last one. Right, so for the last one, let's see which experiments we'll use. Well, we'll just go 1 to 4. Okay, so the rate conveniently has stayed the same, so I'm going to put in times 1 there. The concentration of A has gone down by a factor of 3, so that's a third. So for my rate, I'm putting in, I'll just write this out again, A to the 1, B squared, rate 1, change in A is a third to the 1, so just a third, multiplied by B squared. We're trying to find out what that is. So 1 divided by a third is 3, okay, multiplied, 3 equals B squared. So the square root of 3 is 1.731, so 1.732 is equal to the change in the concentration of B. So if I go from that, multiplied by 1.732, multiplied by 6.6 times 10 to the minus 2, gives me the new concentration of B is 0.114, okay, to 3 significant figures. Okay, so hopefully you can now work out those guys. We're getting into really sort of more exam style questions. I'll put the actual answer up here now. I'll clear my writing off and I'll put the actual answer up and you can have a look at it if you think that you didn't quite get what I was talking about. Okay, so last question that I'm going to do, I'll do another video on actual genuine past paper questions, guys. I'll pull out some of the hard ones in there and we can work through those together. Right, so first thing we've got to deduce the orders. So let's find one where A has gone up threefold, B has not changed, perfect, and the concentration, the change in the rate there has gone up by a factor of, I better work this out because I don't want to get this wrong, 0.00288 divided by 0.00032, that's a factor of 9, so hopefully you can work out that therefore A must be second order. Let's have a look at B then. Okay, now here's the nastiness about this one. There are no experiments where A does not change, so I'm going to have to deal with that. So let's write out what we know so far. Rate equals A, second order, times B, that's what, that's meant to be a question mark, that's what we're working out. So let's put in our relative proportions. So let's take experiment 2 and experiment 3. Experiment 2 to experiment 3, A has gone up by a factor of 2, so it's gone up by a factor of 2 to the 2. Okay, so, and B has gone up by also by a factor of 2 to the x. We're trying to work that out. Now let me just check the rate here. So that's 0.01152 divided by 0.00288. So that's gone up by a factor of 4. So rate's gone up by a factor of 4. A has changed by a factor of 2, doubled, so has B. Okay, so 4 equals 4 times 2 to the x. That's where we are at the minute. Okay, that's come from 2 squared. So 4 divided by 4 equals 2 to the x. Okay, so 4 divided by 4 is, of course, 1. Okay, so 2 to the power of 0 equals the 1. So therefore B is 0 order in this particular instance. Anything to the power of 0 is 1, by the way, for those of you who are not mathematical. So I'm saying therefore that A is first order, sorry, A is second order and B is 0 order. Okay, so let's just check I got that right. Yeah, we did. Okay, then we've got to work out the K value. All right, and for the K value we would just take that and that would be, and I'm ignoring that because that's 0 order. Okay, so I'm just doing 0.0032 divided by 0.12 squared, which is 0.0222. And don't forget your units. We should be good at getting units by now. So that's one that's a little bit different, where we've now experienced a reactant which does 3 sets of experiments where one of those reactants is constantly changing. So we didn't have that sort of comfort or that luxury of having just the reactant that we were investigating only changing. Right, guys, I'll do another video with some past paper questions on it, but I think this video is going on to almost half an hour now, so it's more than long enough. And this one should have tied everything we did previously together. I hope it did. Okay, and I will put the next video on soon.